After working through the previous example, hopefully now everybody's a little more familiar with how we can use those 5 simple rules to sketch a root locus. But now we want to ask ourselves, how can we make that more accurate? How can we get a more accurate picture of what our closed loop poles are doing as we're adjusting our gain? So if we want to have a more accurate picture, there are a few different things that we can do. And so I've alluded to these a little bit in our last video, and so I'm going to go ahead and put up our root locus that we had at the end of the previous video, and we're going to use this to discuss some of these items that we can do. So the first thing, which we again briefly mentioned at the end of the last video, was we can find breakaway and break-in points on our real axis. So we can find our real axis, let's move this down a little bit, so we can find our real axis breakaway and break-in points. And so we'll go up to the plot here in a second, and we'll show where that would be on this particular root locus. So for example, if we're looking up here, we only have a breakaway point, and that's going to be located right here, where our blue curve, which remember is our root locus path, is going from the real axis to becoming some complex number. So it's starting on the real axis here, and then at a certain point, it's breaking away from that real axis. And so we could ask ourselves, why is that important? Well, that's important because that sort of breakaway point, or we could also have a break-in point, is going to be sort of the demarcation between overdamped and underdamped responses. So overdamped versus underdamped. So of course, when it's on the real axis, we have, in that case, 2 real poles, so that means it's going to be an overdamped system. But as soon as it moves off of the real axis, we have an underdamped system. And so the idea of a break-in point is just the same, except the direction of the poles is different. So we would have our pole moving this way, and they would be coming into the real axis at a certain point. So again, same basic idea, just slightly different direction there. So that's item 1. So the second item, which we also discussed briefly at the end of the last video, is we can find our j omega axis crossings. So j omega axis crossings. And so coming back up to our root locus here, we can see there are 2 places where this particular root locus crosses our j omega axis. That's at the top and bottom there. And so again, we ask ourselves, why is this important? Well, we know anything over in our right half plane is going to be unstable, and anything in our left half plane is going to be stable. So by figuring out the gain and other values that correspond to those j omega crossings, we can figure out the threshold between stability and instability. So let's come down here and write that explicitly. So this is important because we are sort of determining that demarcation point between stability and instability. And so under that we can put our stability as a left half plane, our instability is our right half plane. So the third item that we can do to sort of refine this is we can figure out our angles of departure for our complex poles or angles of arrival for complex zeros. So I'm going to kind of combine that and just say we can find angles of departure or arrival. So departure and arrival actually for complex poles and complex zeros respectively. And so this one isn't going to be as important as our other 2 items, 1 and 2. So we're not going to take much, we're not really going to look into this further, but if you're curious about that, you can look at more details to the method of how to do this on page 324 through 326 in the 8th edition text. Just coming back up here to this sketch, we see that we don't have any complex poles or complex zeros in this case, but for instance, sort of ignoring the existing root locus, let's say we had some complex poles here and here. Well, we know that our root locus is originating at closed loop poles of our open loop transfer function, or sorry, it's originating at our poles of our open loop system. So if we had complex poles here, then maybe it's going towards some asymptotes, so maybe it's going towards the same red asymptote shown here and here. And so what we would have then is something that looks like this, but we don't necessarily know what angle we have when we're departing from that pole. And so we could refine our plot a little bit, again, using a method that's described on those pages in the textbook. And then a similar thing would happen if we had a set of complex zeros. So if we had a set of complex zeros like this, except now instead of departing, our root locus is going to be coming in and terminating at that zero. So again, the two items that we're going to focus on are our real axis breakaway and break-in points and our geomega axis crossings. And so in the following videos, we're going to look a little bit more on some techniques on how we can do that. And one thing to note about these two techniques we're going to focus on, as well as this third technique, is a lot of these methods for finding this information can get pretty complicated, or at the very least pretty tedious to do by hand. So as I've been saying throughout this unit, if we can, what we want to do is utilize something like MATLAB or even a calculator to help us out whenever possible. And so again, we'll be going over some of that stuff in class. We'll be talking about how to use MATLAB to help us simplify this root locus process.